Hello friends, welcome to the mathematical room. I am the caretaker. So as I said in the last video, today we are supposed to do permutations and combinations. But before that, what I thought is that we should at least solve some problems that require the principle of mathematical induction. Actually, while solving some problems in set theory, actually not solving problems but rather proving some identities. For example, this one. In set theory, we used induction in the proof, but since the proof was rather complicated, so it may not be so apparent how induction was used. Although I have already showed the proof in its entirety, but the use of induction may be somewhat confusing there. So instead of going through induction every now and then, what I have planned is that today we will solve some simple problems involving induction, and this will give us some practice, but also at the same time it will show what actually induction is, which I think although we understood that here while proving this one, but it still has not sunk inside our heads. So that's what we do today. And but why is this appearing before permutation and combinations? That is because there in permutations and combinations there are some problems which need induction, and induction is a method that we will need again and again in everywhere in mathematics. So let us start with some problems which can be easily proved by induction. So but some simple ones. Okay, for a positive integer or for any positive integer. For any positive integer, n, prove the following. So we are going to start with some problems of the same type, and then we will change the type. So the first one is, it asks that you have to show this. So what does this say? It says that if we add up a few of the first odd positive integers, then we get a square. Do you see how these numbers are 2n minus 1? If you put n equal to 1, 2 times 1 minus 1 is 1. If you put n equal to 2, 2 times 2 minus 1 is 3. Similarly, 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. So that's how it's going. Okay. So that's why the nth term is 2n minus 1. It's the term that appears in the nth place where n is a positive integer. And that has to be, you have to show that if you add all these up, you get n squared. So we are going to show this using induction. Okay, now first of all, the question arises, when do we use induction? Right, we use induction when we are to prove something where there is a variable that is a positive integer. Okay, then we can use induction. Now the solution goes like this. Let me solve this one first, and then we will move on to other problems. So since this is the first one, actually it's not the first time we are using induction, but this is the first one we are using induction for the sake of it. for showing how induction works. So I am again going to write a detailed solution, but this is not how things are written in general. Okay, this is too detailed for the sake of understanding. Now, let Pn denote, or let me define it like this, let Pn be the set of all n such that n is a positive integer and this identity is true. 1 plus 3 plus 5 plus 7 etc. up to 2n minus 1, it gives us n squared. So I define a set, I call it Pn, and it is the set of those positive integers n for which this formula is true. So what I want to show, we want to show P of n is equal to n plus. Actually, I should say what this notation means. N plus is the set of all positive integers. It is not a standard notation, right? I have already told you that the symbol blackboard bold n, sometimes it denotes this set, sometimes it denotes this set, where 0 is also included. But since we have decided to use this symbol n for this set, so for us n plus means the set of positive integers. Or if this looks somewhat strange, we can also write our n has 0, has the element 0, so we don't need 0, so we just simply subtract 0 from it. This is what we have to show. What this means, once I show that Pn is equal to the set of positive integers, that means for all positive integers this is true, and that's what we are supposed to show. Okay, so we have just simply reformulated the problem in terms of set theory. Why? Because this is where I can use mathematical induction. What the induction says is that if I have a set A which is a subset of the set of positive integers that has two properties. One of the properties says that the integer 1 is in A, and the other property says that whenever some integer n is in A, then n plus 1 is in A. If the subset A has these two properties, then the induction principle says that A has to be equal to this, not just any subset but equal to this. So in place of A, now think of P of n. Okay. So this is what we have to show. We have to show that 1 belongs to P of n, and whenever n is in P of n, then the next element n plus 1 is also in P of n. Then by the principle of mathematical induction, this will be equal to the set of all positive integers, thereby proving that this formula is true for all positive integers. So that's what we are going to do. Okay, so we want to show this. For this is the standard way of writing. Okay, for this we apply induction on n. So first we need to show that 1 belongs to Pn. which means what? We have to show that this formula is true for n equal to 1. Now for n equal to 1, what is the left hand side? How many terms are there in the left hand side when n is equal to 1? You see, if you put n equal to 1 here, you get 2 times 1 minus 1, which is 1. So there is only one term here, which is the first one. So the left hand side is 1. What about the right hand side when n is equal to 1? Right hand side is 1 square, which is also equal to 1. So in the case n equal to 1, this formula is true. So that means according to the definition of this set, 1 belongs to P of n. So we are going to write it systematically. Note that one is equal to 1 square. This is not becoming clear in the sense that it's not clear I am writing about this one. Note that, okay, let me write like this: 1 plus 3 plus 5 plus 2n minus 1 is equal to n square holds when n is equal to 1. In fact, this is what we have verified here. You put n equal to 1 on the left hand side, you get 1. You put n equal to 1 on the right hand side, you get 1 square, which is also equal to 1. So at least in this case, the formula is true, which means what? 1 belongs to Pn, or, oh sorry, this notation does not need any, sorry about that. This is not dependent on n, so I should not include n in the notation. S. Okay. So this implies 1 belongs to S. Okay. So we have to actually show that S is equal to this. Why did I confuse that with P of n? That is because P of n is this sentence. S is equal to the set of all n such that P of n is true. But P of n is this sentence, this statement that n is a positive integer and this formula is true. That is P of n. Okay, I mistook that for the set. Anyway, so this implies 1 belongs to S. This is the basis for our induction. Okay, this is where we start. This is the basis for our induction, showing that 1 belongs to the set S in question is called the basis of the induction. Now assume n belongs to S for some n belonging to n. Next, what do we have to show? We have to show that n belongs to S implies n plus 1 belongs to S. This is what we have to show next. So to show this, we first assume this. This implies this means you assume the hypothesis and then get the conclusion. Remember, this is an implication, so this is hypothesis and this is conclusion. This hypothesis has a special name. It's called the induction hypothesis. Okay. Now assume n belongs to S for some n belonging to n. I have to rub these things off to make space. Okay, so I continue from here. So I can write this is the induction hypothesis. Of course, I have written it within brackets because we don't write it, okay? This is for our knowledge. This thing that we assume after having the basis is called induction hypothesis, okay? This means, okay, what does this mean? N belongs to S. S is the set of those positive integers for which that formula is true. So this means 1 plus 3 plus 5 plus etc. You can write 7 or you may not write 7. I have already said this, I think, once, that how many terms you write when there is an ellipsis is up to you. Just the pattern of the terms should be clear. So our induction hypothesis just means this, but not for all n, for some n. Okay, for some n we have assumed that this is true. We have assumed that this holds, and now we want to prove the same statement for n plus 1. Okay, now what is this left hand side when you have n plus 1 in place of n? Sure, the sum will start like this, and then nth term is what? 2n minus 1. But you want one more term, okay, to write the case, to write this expression for n plus 1 terms. These are n terms. So the next term you just simply write n plus 1 in place of n. Okay, be careful. We are writing n plus 1 in place of n. That is called, it is already 2n. So 2 times n plus 1 minus 1. Okay. We have to show that this is equal to n plus 1 square. That is the formula when you have n plus 1 in place of n. Okay. Now for that, we already have this one given to us, and this sum is here, it's a part of the whole sum. So this is equal to n square plus 2 times n plus 1 minus 1. So what do you get from here? N square plus 2 times n plus 2 minus 1, or n square plus 2n plus 1, which is nothing but n plus 1 whole square. So you see that actually the assumption that the formula is true for n implies that it is also true for n plus 1. This implies n plus 1 belongs to S. Okay, so this assumption, this hypothesis has led us to this conclusion. So the second condition for induction has also been shown to be true. That's why by induction, hence by induction, S is equal to the set of all positive integers. Okay. Now you reinterpret this set theoretic identity in terms of the actual question that we have. It simply means that the set of those positive integers for which the given formula is true is the set of all positive integers. In other words, the formula is true for all n, where n is a positive integer. And that's how we write an induction proof. Now, actually when we write a proof or a solution involving induction, we don't mention S. Okay. You remember we first defined S, I mistakenly wrote it as P of n, so that one is S, that's it. We don't write that. We start from here. We start the solution from here. For this means for this solution we apply induction on n. Note that this holds when n is equal to 1. This implies 1 belongs to S. In place of this, we write this implies the formula is true for n equal to 1. This is what we write. Since we haven't defined the set S, I mean, we can define, but that is only for the purposes of understanding. When we write an actual solution, there we don't mention S. It's there in the background. It's there for us, but we don't usually write that. So we write in not in terms of set, but in terms of the actual thing that we are supposed to prove. So this implies the formula is true for n. So we start the solution here. For this solution, we apply induction on n. We have shown that the formula is true for n equal to 1. This is the basis for our induction. This part is also not written. It's omitted. We know this is the basis. Okay, this is for your information. Now assume in place of n belongs to S. Now assume that the formula is true for some n belonging to n. This statement and this statement are one and the same. Okay, n being in S and the formula being true for that n are the same. Okay, so that's why you see sometimes defining set makes the job easy for us, at least for the purpose of writing. Instead of this small statement, we have to write this. But sometimes it becomes cumbersome to always keep on defining sets to apply induction. That's why we don't usually write sets. Okay, so this part is written here for some n. This is the induction hypothesis. This part is also not needed. Okay, this means, and after that everything is the same except the last one, of course. Hence by induction, instead of writing this, the formula is true for all n greater than or equal to 1. Usually that's how it's written, where it's understood that n is an integer. If you simply write n greater than or equal to 1 without any context whatsoever, then n is a real number. Okay, so it may not make sense. But in this context, since n is a positive integer, so this makes sense. And we understand that n is a positive integer. N cannot be, for example, 3.2, it cannot be like that. Okay, so since this looks rather messy, so let me once more just simply show you the proof without S, outline of the proof without S. So we start the solution of the proof like this. For this we apply induction on n. Okay, note that the formula is true for n equal to 1. So this is the basis, don't write that. Okay, next assume that the formula is true for some n belonging to n. So this means then after that you carry out the calculation which gives you this. Okay, so hence the formula is true for n plus 1. So by induction, the formula is true for all n greater than or equal to 1. Okay, so this is the general outline of the proof, and this is how we approach all the problems which require mathematical induction for their solution. Without mentioning that set S. That set S is in the background, and when we are applying induction, we know that we are actually applying induction on that set, for that set, because the statement of induction principle involves a subset of the set of positive integers, but that should stay in the background. So this is how we are going to write the other solutions. So let us now move on to some other problems. Okay, and one more thing that I should mention here is that while solving a problem using induction, both the basis for induction and showing that the induction step is true. Induction step means showing that something is true for n implies it is true for n plus 1. That is called induction step. Showing that it is true for n plus 1 based on its truth for n, that is called induction step. So there is basis and there is induction step. Both of them have to be shown in order for the induction to be effectively proving that the formula is true for all n. Let me show you an example where things go wrong. You see, without proving the basis, if we just show the induction step, let me try to prove this wrong formula. Same sum, but instead of n square, suppose someone is suggesting this n square plus 3. This is clearly wrong. But when we look at a formula about which we don't know, this is rather simple, so we can maybe put some values of n and see that it is true. But in some cases, things may be so complicated that even verifying that the formula is true for some given value of n, that task may be a daunting task. Okay. So assume that this is given to you and you want to prove this using induction, but suppose someone forgets to prove the basis and straight away moves to show that the induction step is true. So what will he do? He will assume that the formula is true for n, which means this is true for some n belonging to the set of positive integers. Next, then for carrying out the induction step, what he will do, same like before. We write the sum for n plus 1 terms plus 2 times n plus 1 minus 1. So this part, this sum, again same method, in its place we can write n square plus 3 plus, now what do we have here, 2n plus 2 minus 1, that means plus 1. Okay, so you can see that this can also be written like this, plus 3, which is n plus 1 whole square plus 3. So you see that the induction step is correct. If you assume that the formula is true for n, then it is true for n plus 1. But the problem is that since the basis has not been checked, we don't really know whether the formula is true for any n at all. In fact, it is not true for any n. Because we have already proved that this is equal to n square, not n square plus 3. Okay, and n square is never equal to n square plus 3. So that's why forgetting to show that the basis is true can lead you to a wrong conclusion like this, where a false assumption leads you to a false assumption. But note one thing carefully, although the formula is true, but the implication that this implies this, although the formula is false, but the implication that this implies this is true. Okay, because false can imply false, it is vacuously true. So that's why we have to show both the basis as well as the induction step in order for the induction to work. Okay, now let's move on to the next problem. Again, same, show for that the following is true for all positive integers n, 3 square etc. plus n square is equal to n times n plus 1 times 2n plus 1 divided by 6. Okay, this one we have to show by induction. Now that I have carried out the proof of one of the problems or the solution of one of the problems involving both the set and also not involving the set. So here I will be sketchy. Okay. First you show that the basis is true, which is nothing but showing that the formula is true when n is equal to 1. Okay, you have to write all the things just like how we wrote in the previous solution, but here I am not writing, I am just showing the mathematical details. So what is the left hand side when n is equal to 1? Left hand side is 1 square, which is 1. What is the right hand side? Right hand side is 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. So this is equal to, or let me write it here, 2 times 2 plus 1, 3 divided by 6 is equal to 1. So we see that when n is equal to 1, these two are equal. That is, the formula holds for n equal to 1. So this is the basis. Although we should not write that this is the basis, we just simply write hence the formula is true for n equal to 1. Now assume that it is true for some n greater than or equal to 1. You can, instead of writing that n is a positive integer, you can write like this also. Assume that this is true for some n greater than or equal to 1. As I have already told, n is assumed to be a positive integer, since that's what we are concerned about here. Okay, fractional n, that does not make sense, it's out of context. Now we have to prove that this is true for n plus 1 terms. So then you start with the sum. Since we want n plus 1 terms, we are going to write an extra term. Okay. You can see that we are always starting with the left hand side. That's obviously not necessary. You can start from any side you want. In fact, you can start from here also. But that will be somewhat more complicated. As you solve more and more of this type of problems, you will know what is easier than the other. Okay, what approach is easier. So in this sum, the sum of the first n terms is already given to us. It's assumed. So n times n plus 1 times 2n plus 1 divided by 6 plus we have this extra term. Now what can we do? We can take n plus 1 divided by 6 as a common term outside. If we do this, what, okay, n plus 1 by 6 we already have here. So it will be n into 2n plus 1 plus n plus 1 we have taken out, 6 was not available here. So instead you can write like this, 6 divided by 6. Then 1 6 will be left there and you will have n plus 1. Okay. Okay, so now this is equal to n plus 1 divided by 6. Shall I have space for this calculation, or let me wrap this part up and continue from here? N plus 1 divided by 6. Okay, so if we multiply and simplify this, we get 2n square plus n plus 6n gives us 7n plus 6. Okay, now